All right, so let's go over these here. And they're both pretty challenging problems because they're not just routine, here's the lengths, find the area. In number one, they give us the area is 51.25. And then we have to work backwards to find one of the bases. So I like to think of this as a backwards problem. The first thing I'm going to start with is the fact that they give us a trapezoid. Okay, and maybe I should have put parallel lines here. Um, but the very first thing I do is I write out the formula. 1/2 base 1 plus base 2 times the height. And then I'm going to plug in everything that I know. I know the area is 51.25. I know base, I got to find base 1, so I know base 2. I'm going to leave base 1, and I might just call this B instead of B1 so we don't get confused with an extra number in there. It doesn't really matter. And then the height is the distance between the bases. All right. Now, there's a couple of ways to solve this. This is the way that my brain works. I really don't love having this 1/2 here. So I'm going to move it over to the other side. And one way to undo a times by 1/2 is to times by the reciprocal of 2. So the 1/2s reduce out. And then I've got 51.25. If I double that, I get 102.5. Now, you could distribute if you would like, or you could divide both sides by 5. Doesn't matter. I'm going to divide by 5, and that leaves the base plus 8 is equal to 20.5. And then my last step would be to subtract 8. And we get 12.5. And then double check your answer. Did you include the units? Now notice, we didn't put them here, but we said the area was units squared, which means all of the other lengths would just be regular units. So you could put U, doesn't really matter. I usually just put a U. But notice it isn't squared because this is a single length. This is base 1. So we got 12.5. All right, so now let's look at number 2. Now number 2 is really tricky. It is still a backwards problem, but they don't give us any side lengths. The only hint I gave you that this was a rhombus. However, it's actually more than just a rhombus, but if we know that the diagonals are perpendicular, that's what kind of clued me in that this is a rhombus. And these lengths are congruent. That means this length is congruent to this length, and this length is congruent to this length, because in a rhombus, diagonals bisect each other, and the fact that these two are congruent means they're all the same. So there's a couple ways you can think of this. I think of it algebraically. I think if I don't know what AB is, I'm going to call that X. Well, that means that BC is X, but that means that the other two lengths are X as well. So if it's a rhombus, I'm thinking the area formula for a rhombus is 1/2 diagonal 1 times diagonal 2. And then I know that the area is 72 units squared. But then the diagonals go from A all the way to this endpoint, and that's the sum of these two pieces. So this full length is 2x, and this full length over here, left to right, that's diagonal 2, that's also 2x. So now we can kind of simplify however you want. I'm going to multiply the x's together. X times x is x squared. A 2x and a 2x, 2 times 2 is 4, but then I'm going to cut that in half, so that'll be 2. And now, algebraically, we have to get rid of the 2 first. I get 36 equals x squared. And then to get rid of the square, we take the square root. And that tells me that officially we do get two answers. We get a +6 and we get a -6. We're only going to accept the +6 because it's a length and length is positive. So find the length of AB. Well, AB is the length from here to here, and that's what we called x. So to answer the final question, AB is 6 units. Okay, so kind of some challenging ones, which is really good for us to look at. It's more than just, do you know the formula, right? It is, do you know the formula, but then do you know the pieces and can you work backwards? And this one was extra difficult because we didn't give you those values. All right, really quick, I want to give you guys a shout out here and say thank you. I was updating grades the last couple of days, and I noticed specifically on section 11.2, you did a phenomenal job of showing your work, drawing the pictures. I mean, it looked like the work that I was modeling for you, and that is exactly what I want to see. So keep that up. That's the stuff that we're looking for. And usually when I am grading homework, it's 3, 4, 5 kids just put answers down and they don't show your work. I would say almost 100% of us had shown the exact work that needed to be shown, and that's rare. So I thank you for that, and I really do appreciate your hard work. All right, I love this quote: "Intelligence plus character, that is the goal of a true education." Right? So we're trying to teach you. I mean, it's not as it's harder from distance learning, but we're trying to teach you how to be and how to think creatively and basically gain intelligence. But we're also teaching character, and that goes on the side of your ownership of your own work too. All right, we are starting a unit that is a little different. It's section 11.3, and the learning target relates back to this idea of similarity. So just so you understand, we are revisiting some ideas with scale factor, and then we're going to use scale factor to determine lengths of perimeters and area with similar figures. So we're kind of making a connection here between how did scale factor relate to perimeter and area. And the first thing I'll just kind of quickly mention here, when we learned scale factor way back in chapter 6, we called the scale factor A to B. That was how one side compared to another. We're going to review that here quickly. So look at, even before I show you anything else, you should hopefully have a really strong understanding of, ooh, similar triangles, right? We have that little symbol here, similar triangles. I could compare side lengths. I could compare PQ to TU, and I could compare that side to that side if they gave me lengths, and I could find the scale factor. Or if PQ isn't available, I could use QR, and I could compare that to UV. Or if those lengths aren't available, I could even go P to R, and that would match with T to V. So that's just a quick review of how we can use the similarity statements to match up sides. And if they are similar, that means they have to have a scale factor. So our goal is to use the fact that these triangles are similar, and we want to find the perimeter and the area for both triangles. Now, we don't know the connection yet between scale factor and area or perimeter. So what we have to do is I'd like you to, let's see, I'd like you to kind of work on this problem kind of as a warm-up, or go ahead and try it and answer these 3 questions. Find the ratio of sides, which, by the way, the ratio of sides is the scale factor. All right, so find the ratio of sides, and then use the value to find the missing side lengths so you can find the perimeter and the area. So I'll give you a couple minutes to work through this, and then we'll go through it. You do not have to chat this answer. Okay, just work through it, and then we'll go over it in a couple minutes. All right, so to start, we want to find the ratio of sides. Well, we have the similarity statement, and I want to compare the sides that I know match up. And so the only thing that I know on this side is 30, and that's US. Oh, interesting. Sorry, this should be a, didn't catch that. This should be PQRTUS. I don't know how that got switched. Hopefully that didn't confuse anybody, but if I match US, that has to match with QR. So my scale factor, and it doesn't matter, they don't tell me specifically which triangle if I go from the small to big, so I'm going to use the statement. I'm going to take QR over US, so 20 over 30, and then each one of those can be divisible by 10. So when I reduce that, my scale factor is 2/3, or remember, we can write it as 2 to 3 as a ratio. Well, that 2 to 3 is the AB, and we're going to talk about that later on. So it's just important for us to know when we say AB, we're talking about the scale factor. All right?
Does the smallest number always go on top?
If notice how the triangle PQR is the smaller triangle, so that was written first. If this was flipped around, then I would put the 30 on top and the 20 on bottom. But it really doesn't matter. If you said your answer was 3 to 2, that just means you took the big one first and put the small one on the bottom. And it's okay because they didn't tell us the specific way to set it up. So what I want to do then is I want to find the missing side lengths. And let's call this side X and maybe this side Y. Because then I'm going to find the perimeters and the area. And actually, I should find this piece here as well. Notice this is a 3, 4, 5. So if you recognize it, we've got 5 times 4 gave me 20. 4 times 4 gave me 16. So this would have to be a 3, 4, 5, but it's a multiple of 4. So I know for sure that this side length is 12. If you didn't see that, then you would have to do Pythagorean theorem. Okay, and Pythagorean theorem will also get you to this side to be 12. So now I know all the sides of the smaller triangle, but I can't find the X and Y unless I do some of that work from similar triangles. So that's what I'm going to do over here. I'm going to think of this as side work. So I want to find X. Well, let's look. UT matches with PR, but I started with, QP. So I'm matching 12 to X. So 12 over X has to equal 20 over 30. But instead of writing 20 over 30, don't we know that that's the scale factor, 2/3? So every ratio that I set up from the small triangle to the big triangle has to equal 2/3. So there's the first one. I'm going to cross multiply and solve that. But let's set up the y value as well. 16 compared to y. So 16 over y also has to equal the scale factor of 2/3. So those are my two cross multiply and solve. So if I do 3 times 12, that's 36. That's equal to 2x. If I divide by 2, x is equal to 18. And then here I get 3 to 16. So 3 times 16, that's 30, plus 18, that's 48, equals 2y. So y has to be 24. So hopefully you remember doing that stuff from similar triangle time. Well, now I can find the perimeter of each shape. Right? Just add them up. I'm going to do that inside here and just say, okay, well, what is the perimeter? 12 plus 16, that's 28. 28 plus 20 is 48. And that would just be regular units. We didn't have any units here, so I'm going to call that just units. And then if we do the same thing over here, 18 plus 24, that's 42. 42 plus 30 is 72. So now it says find the ratio of the perimeters. And we did not tell you to take the small one to the big one or the big one to the small one. So I'm just going to do PQR. And notice if your ratio is flipped or reciprocated to mine, that's okay. So ratio of the perimeters is 48 over 72. But as we have done with every ratio, we're going to reduce that down. So I know for sure I can divide by 6. I could probably divide by 12. And if actually I can divide even more. What goes into that evenly? 24. 24 goes into each one. But notice, when it reduces down, the ratio of the perimeters is actually the same thing as our scale factor, or the ratio of sides. And that's one of the theorems we need to talk about today. So we just kind of discovered that on our own. Okay, now I also need to find the areas. I want to find the ratio of the areas. So I got to find the area of each triangle. And I might do that off to the side here. I don't have a lot of space, but I know that a triangle area is 1/2 base times height. The base I can call 16. The height is 12, and I know that because of the 90-degree angle. So 1/2 of 16 is 8. 8 times 12 is 96. And then I'll just call that units squared. And then I got to do the same thing over here. Again, I don't have enough room. So the base is 24, the height is 18, and 1/2 of 24 is 12. 12 times 18 is 216. So find the ratio of the areas. Since I took my scale factor as the small triangle to the big triangle, and I did the same with the ratio of the perimeters, I want to do the same comparison with the areas. So if you had it flipped, that's fine. Just make sure yours is consistent for each problem. So now I got to reduce this fraction down, and I think we talked about this. I'll show you quickly, if you have your calculator, how you can reduce fractions very quickly. So you take, what was it, 96 divided by 216, hit enter, and we don't want decimals, so we want to go back to math. So once you get the decimal, hit the math button, and then your first option is fraction, and you just hit enter, and it'll take that decimal answer and it'll turn it into a fraction. So 4/9. So now this is something that's kind of interesting as well. The ratio of the area is not the same as the scale factor or the same as the ratio of the perimeters, but it is related. Maybe in the chat, or you could unmute yourself if you'd like. Does anybody see the connection? How does the ratio of the areas relate to the ratio of sides or the ratio of the perimeter?
Is it because like it's like kind of double, right? It's like if you like divide two, it just gives you like two on top of like the side end.
Yeah, so in this case, we have to be careful when we use the word doubled or timesing by 2, because if I times the top by 2, I get 4, but if I times the bottom by 2, I get 6. But a couple people in the chat had said it's multiplied by itself or it's squared. And you're right, you guys are right on. That is squared. So notice another way to write this ratio, which will be very helpful. Another way to write 4 is 2 squared. And another way to write 9 is 3 squared. And that's the connection we kind of want to make, is that the ratio of the areas of similar shapes, it has to be similar, is the scale factor squared. So if I take the 2/3 and square it, that gives me the ratio of these areas. Now what that actually leads towards is the fact that all this extra work that I did right here to find x and to find y, I actually don't need to do that anymore as long as I know the scale factor and the area of one side. I can find the area and the perimeter of another shape. And that's our goal today. Okay, so here's the official. What's that?
Are your side lengths and perimeters going to be the same ratio all the time?
Yes, yep. If the shapes are similar, and it doesn't matter if it's triangles, right? We know it could be any shape. So if I have two similar shapes, the ratio of sides and the ratio of perimeters will always be the same, and the ratio of the areas will be that value squared. And that's what this theorem officially states right here. So if you would like to write this down, I'd kind of recommend it. I don't know if I draw the picture. I don't think you really need the picture, but it says if the lengths of corresponding sides of similar polygons are in the ratio of A to B, that's your scale factor. So if you know that the sides are in the ratio of A to B, then the ratio of the areas has to be A squared to B squared. So that was basically what we just discovered. And we've kind of introduced this idea before. I don't think the pictures really do justice. The only things the picture shows here is that when we say A to B, it's the ratio of sides, right? So it's this side length to this side length, and then you always reduce it, so it is your scale factor. And as you had mentioned in the chat, the scale factor squared. So here's the way I think of this. Remember when we found area and we wrote the units? Our units were always units squared. Right? So if I have the ratio of sides, the ratio of sides is just regular units. That's A to B. If I'm dealing with area, then I have to square the scale factor. Okay? Down here, this blue part is not officially part of this theorem, but we saw this and kind of developed it before. The ratio of the perimeters is the same as the ratio of sides. Right? Or it's the scale factor, and we saw that as well. So I always like to do kind of the problem we just did before this is you can find these relationships. You can look at these patterns by just exploring problems and using the material that we learned in the past. And that way it's just not a new fact. We just kind of stumbled upon it ourselves. So this is the big idea for today. The question that's left is how do we use this knowledge? Now that I know that the areas are just the scale factor squared, how do I use that to find out maybe the area of one piece if I know the area of another? I'll give you another minute to write this stuff down. Okay, hopefully that was enough time. If not, let me know. I can jump back here. But the goal today is to figure out how do we use this. So we're going to treat a problem very similar to what we just had, where we know kind of everything about one shape and we don't know a side length of another. So I'll give you a second to write this. Okay, so let's go through these quick just to kind of see where you're at. So find the value of x. This is really just an old problem from the past. What we want to do is we want to compare the side lengths that match up. So I would say 6 over x. I compare small to large. You could go large to small and have x over 6. But however you compare that, then you're going to compare it to the other two sides, which would be 10 over 25. But that 10 over 25 can be reduced to a scale factor, and we're going to need that scale factor anyways. So I might do this instead. I might say 6 over x, and then if I just divide each one of these by 5 is 2/5. So that 2/5 is the scale factor. Okay, and then this is a really quick cross multiply. 6 times 5 is 30. 2 times x, and then divide by 2. And we get x equals 15. Okay, 15 units, whatever it is. So nothing special there. But now, the second part says, find the ratio of side lengths. And I want to just kind of go with our thought process we had on the last example. The ratio of sides is your scale factor, right? All that is the A to B. So we know that the ratio of sides is 2 to 5. It's your scale factor. The ratio of perimeters, now you could, if you wanted to, you could take the fact that this side is 10 and this side is 10 and find the perimeter, and then find this side is 15 and this is 25. You could do the perimeters, you could compare them, but the theorem we just talked about said the ratio of the perimeters will always be equal to the scale factor or the ratio of sides. So we don't need to find the perimeter of either of these two if we already know what the scale factor is, and that is the ratio of the perimeters. And then the special one was, what is the ratio? So find the ratio of the areas. That's where you square the ratio of the sides. So instead of being 2 to 5, we got to square both of them, and that will turn into the ratio of 4 to 25. Okay, so now, how do I use the new theorem? How do we do part 3? Use the new theorem to find the area of the larger shape. Well, to do that, I need to know the area of the small shape, and the area of the small shape is 6 times 10, or 60. Right, so I had to find that. That's 60 units squared. But how do I do that if I don't want to find the area of the big one? Right, how do I use the new theorem? Well, we're going to take the ratio of the areas. We're going to take the 4 over 25 and that ratio has to equal the ratio of the area, right? Area of the small one to the area of the large one. I'm going to add a couple little notes here just so we are kind of looking at what we're doing. So I'm going to compare the area of the small shape over the area of the large shape. And then this whole blue piece this is the ratio of the areas, right? That's what we talked about right here. 25 or 4 over 25 is the ratio of the areas. So all it is another cross multiplication problem. Nothing super special. The numbers are a little bit bigger. Right? 4 times A, and then 25 times 60, which is 1,500. And then divide by 4. Okay. Now I know what you're thinking. Why would I do all that? That seems like a lot of work when I already found the other side length. Well, we're basically giving you an example like this so you can confirm that it works. So is the area of the large shape 375? Well, let's just do a quick check. Does 15 times 25 give me 375? 25 times 15 is equal to 375. So this confirms that the area is using the ratio of the areas also works. Okay. Now, if you're thinking, well, I don't need to know this because I'll just do it the long way every time, then I'll say, what about a problem like this next one? Okay. Now notice this one right here. We have to know the two shapes are similar. Find the area of the smaller hexagon. We're going to do this one together, so don't work ahead, but I'd like you to just draw the pictures the best you can. If you want a hint for how to draw nice hexagons, is put 6 dots in a circle, kind of, as equally as spaced apart as you can, and then connect them. That's a pretty good way to draw hexagons. Sometimes that's hard. I mean, look at mine. It's not great. But if you try to draw it like this, sometimes it doesn't match out as perfectly. Anyways, that's a little hint. Okay, let's look at this one, and I'll show you how this one goes. Again, the key part is that we know the shapes are similar. Without knowing they're similar, we can't do any of this work. So what do we want to do first? First thing, we want to find the scale factor, which, remember, that's the A to B ratio. Well, the scale factor is just comparing the sides. So I can think of this side as A, and this side as B. And let me see if I can color coordinate this. This will be perfect. So there's the scale factor, which we can write it this way, or I prefer to write it as a fraction, and you'll see why. All right, there's my scale factor. Now, what do we know? Okay, the second thing is that the ratio of the areas is a squared b squared, right? That's squaring the scale factor. So I'm going to plug in the 7, because that's what A is. And then I'm going to plug in the B, which is 9. And this is what the ratio of the areas have to equal. Right? So what I'm going to do then is I need to find the ratio of, I need to find the small area, but I know the large one. So I'm going to put an A here, and this is a capital A, and this is the area of the small shape over the area of the large shape. Well, notice, all I did was take the a squared to b squared, and I compared that to the ratios of the actual areas, because these have to be equal. So then, we know that 7 squared is 49. I know that 8 squared is 81, and that has to equal a over 210. And then it's just grab your calculator, cross multiply, and you could do all of this in your calculator. Once you set this up, I don't need to see this work right here. And then divide by 81. And you might get decimal answers, which is completely fine. In that case, we would round to the nearest third decimal. Include your units. And there it is. That is the area of the small shape, which is kind of cool. I don't know if you guys appreciate what we just did. We took the knowledge of one shape, knowing the area and side length, and we were able to use the ratio to find the area of the small one only by knowing one side length. I don't know anything else about this shape other than it's similar, but yet we were still able to find the side length. Okay. Really quick, I don't want you to write this. I'm going to do it really fast. I just want to show you this. Let's say that this was a regular hexagon, right? So if that's the case, all of these sides are 9, and there's 6 of them. So the perimeter would be 6 times 9, or 54 inches. Okay. Now, what if I wanted to find the perimeter of this one without doing, I know that these would all be 7, right? So 7 times 6 is 42. So I know the answer is 42, but watch how this would come about. How would I do it? I would take the scale factor, 7 to 9, is equal to the perimeter of the small one over the perimeter of the large one. So notice this isn't squared because it's the perimeter. So then I would just cross multiply. And 7 times 54 is 378. And if I divide that by 9, I get 42. So this is just a quick example of how we would do the perimeter one. Versus area. The only difference is area was the scale factor squared, and perimeter is just the regular scale factor. All right, we got one last problem. It says the ratio of two areas of similar figures is 20 to 36. Find the ratio of their sides. So we're going to do this together because every year kids make this much harder than it needs to be. So here's the way I think of it. In the directions, they say the ratio of the areas is our equal sign, is 20 to 36. So, okay, let's think about what that is. Ratio of areas. Right away, my brain goes to, that's the a squared over b squared. So I'm going to write it as a fraction. By the way, if you ever see this, hopefully you're remembering is the equal sign in words. And then 20 over 36. And then what I want to find, I want to find the ratio of their side lengths. So we want to find what is just the a to b, which means I got to get rid of the squares. Before you do that, okay, you can make your life a little easier if you reduce. 20 over 36, you can excuse me, you can divide each one by 4 and change that into 5/9. Okay, so now the question is, how do I turn the a squared and b squared, how do I make that into just an a over b? Well, to do that, we want to take the square root, but I can't just to take the square root of one side, I have to do it to all ratios. So it's not super friendly. The top part, square root of 5 doesn't reduce down, but we know the square root of 9 turns into 3. And this is my ratio of sides. Or, remember, it's also called the scale factor. And this is also the ratio of perimeters. Spelling is hard. Hold on. There we go. So not only did we find the ratio of the perimeters, found the ratio of sides, we also found the scale factor. All three of those things are the ratio of A to B. So if you're given the ratio of the areas, all you do is reduce and then take the square root. So that's all we have tonight. Your homework is 11.3. I will post these notes because I think you might want to look back on some of them as you're doing the homework, or you have the notes in your notebook. Homework is 11.3. It's from the textbook. Please make sure that it says 10 through 16 even. You're only doing the evens. That'll reduce the amount of problems you have to do. If you have any questions, I'll be available in my office hours. Please feel free to stop in. Otherwise, have a great weekend and make sure you post this to Schoology when you're done. The answers are also on Schoology. You can check them as you go. Adios.